Okay, I think we can start. So good morning or afternoon, depending where you are in the world. The Brazilian Physical Society is starting a series of web-based colloquia entitled Distinguished Colloquia Series that we hope will benefit our 6,000 members across the country and the physics community at large. It is a great honor to open this series with Professor Steven Weinberg from University of Texas, Austin. Professor Weinberg has been one of the most influential physicists for the past 5 or 6 decades. He has done fundamental contributions in and wrote books on topics such as field theory, cosmology, quantum mechanics, in addition to popular books such as Dreams of a Final Theory, the recent To Explain the World on the Rise of the Scientific Method, and in 1977, the first 3 minutes, which has inspired a generation of physicists, including me. In 1967, 50 years ago, he published the article A Model of Leptons, which laid the foundation for the Standard Model of particle physics, and for which he shared the 1979 Nobel Prize with Abdus Salam and Sheldon Glashow. One could spend hours talking about the large number of accomplishments of Professor Weinberg, but I think you're all eager to hear his talk. But before starting, I want to say that we are recording this, and the video is going to be available at the site of Brazilian Physical Society soon, and that the questions, we're taking questions, but you have to write the questions in the chat, and then I read them to Professor Weinberg. So Professor Weinberg, thank you very much for accepting our invitation, and the stage is yours.
Well, good morning. Thank you very much for giving me this opportunity to lecture to your society without actually having to get on an airplane, which is increasingly something I try to avoid. Looking back to when I was a graduate student, I recall a time of great confusion, both in elementary particle physics and in cosmology. A period when you could almost describe the opinions of physicists and astronomers as ideologies. And as often happens with the ideologies, there were clashes and scientists were not always polite to each other. In the years since then, there has developed to a remarkable degree in both areas a consensus. I gave this consensus originally in cosmology the name Standard Model. Standard in the sense that these theories of cosmology, elementary particle physics, we can agree to accept as a basis for discussion without committing ourselves to the idea that these are final truths. I think this kind of consensus is important. It doesn't drive out innovation or new ideas. Rather, it provides a basis for a common understanding of experimental data so that at the same time, the theoretical consensus can inspire new experiments and interpret experiments as they are done. And in this way, we will learn how to go beyond our present consensus, how to go beyond these standard models. I'm going to begin by talking about cosmology and then elementary particle physics. But in the end, I'll have to bring them together in my talk, as in fact they have come together in our work in physics and astronomy. In the 1930s, first cosmology. In the 1930s, cosmology largely consisted of a study of the expansion of the universe, measurements of the rate at which distant galaxies are rushing apart from each other and of how that rate is changing with time. Cosmology was even called a search for two numbers. It entered a modern phase in 1964 with the more or less accidental discovery of the cosmic microwave radiation background, a background of radiation whose effective temperature was a few degrees above absolute zero. Actually, it had been anticipated theoretically through work in 1948, 49, when it was realized that the early universe, when matter was all crunched together and hot, had to be very hot. And to be specific, there had to be a large ratio of photons in the radiation to nuclear particles, neutrons and protons, to prevent all the matter of the universe from forming heavy elements, leaving essentially no hydrogen left, in contradiction to the experimental fact that most of the matter of the universe, the ordinary nuclear matter, is hydrogen, not heavier elements. But this was lost sight of. For some reason, astrophysicists passed over the obvious conclusion that if the universe is expanding and cooling, there must have been a time when it was hot and dense, much hotter and denser than now. And this finally was realized experimentally, as I said, in 1964. This radiation came under intense study. It was found that its temperature is 2.725 degrees Kelvin above absolute zero. And it was black body radiation, the same distribution of energy with frequency as you get from the thermal radiation emitted by an opaque or black body. And this was the basis of theoretical calculations, which showed that the universe cooled to the point where helium and heavier elements like lithium could form at the end of the first 3 minutes. And then the universe went on expanding and cooling, at first too hot for ordinary atoms to form, because free electrons scatter radiation very effectively. The universe then was opaque to radiation. We cannot see into this period, but when the universe reached an age of 380,000 years, it became cool enough for the electrons to fall into orbits around protons and helium nuclei. The universe became transparent and entered the period of what we see now, the Big Bang. The abundances of various chemical elements were calculated and found to agree pretty well with what we observe in nature, with some continued problem with lithium. Originally, this radiation was recognized as cosmological because it was uniform in the sky. It wasn't coming from the center of our galaxy or from anywhere on the surface of the Earth. But astrophysicists knew it couldn't be perfectly uniform because, after all, it had to evolve into the non-uniformities we see in the sky, galaxies, clusters of galaxies, and so on. That led to a definite expectation of inhomogeneities in the temperature of this radiation, which we are in effect observing as it was at the end of the first 380,000 years, but cooled by the expansion of the universe since then. And indeed, in 1992, the Cosmic Background Explorer satellite discovered these expected inhomogeneities. Following this, we have had a standard Big Bang cosmology, which has driven out its competitors like the steady state theory and has become the standard model of cosmology. In contrast to the development of cosmology, where it was shortage of data that inhibited progress, in the development of elementary particle physics, we had plenty of data. We were drowning in data. What we had was an absence of theories that we could actually use to understand the data. Going back to the 1950s and 1960s, we had one example of the kind of theory that we would like. It was quantum electrodynamics, the theory of electrons and positrons and photons, which, as it had developed in the 1930s and 1940s, had evolved to the point where we could make extremely precise calculations which agreed with great accuracy with observation. It was a quantum field theory in which the fundamental constituents of nature were recognized as fields, the field of electromagnetism, which of course had been known for well over a century, and the field of the electron, whose quanta are the individual electrons. This was the goal that many of us felt we had to pursue, a quantum field theory that would account for all the phenomena we were seeing in our laboratories. And so it has turned out, but it hasn't been easy. There were two other classes of interaction that were well known in the 1950s. They were, first of all, the weak interactions. These are the interactions that occasionally in a nucleus allow a neutron to turn into a proton or vice versa, emitting an electron or a positron and a neutrino or an antineutrino, and hence responsible for nuclear beta decay. We had a quantum field theory of this weak interaction, which goes back to Enrico Fermi's work in the early 1930s. And this quantum field theory agreed with the data on nuclear beta decay and on the weak interactions of the newly discovered new classes of elementary particles, but only in the lowest order of perturbation theory. When it was pushed beyond the lowest order to calculate the rates of processes which we weren't actually observing, but which we knew had to exist, we got nonsense. It wasn't just that, the results of the calculations disagreed with observations. There were no observations. I'm thinking of processes like neutrino-neutrino scattering. The calculations gave results, say, for the probability of these reactions that were infinite, clearly absurd, and whether you knew anything about the actual rates or not, the actual rates would not be infinite. So we had no believable, reliable quantum field theory of the weak interactions. As far as the strong interactions, we had as many theories as you like. We could invent countless theories that were perfectly all right as far as not producing infinities, but that could not be used because the strong interactions are strong. And the strength of the interactions meant that lowest order perturbation theory could not be trusted. And in fact, no order of perturbation theory could be trusted. The rate for any process would be given by an infinite sum, every term of which was comparable to every other term. Not a very good basis for doing calculations. So what to do? Some of us were intrigued by an aspect of the success of quantum electrodynamics, and that was called renormalizability. Quantum electrodynamics also exhibited infinities, but the theory was so simple that the infinities could only occur in certain definite places in our calculations, just such places where they could be canceled by a redefinition of the parameters of the theory, the charge of the electron and the mass of the electron. So that after correctly identifying what is the actual physical mass and charge of the electron, the infinities would all be seen to cancel. Only a very limited class of quantum field theories are renormalizable in this sense, that infinities only occur in a finite small number of places in the calculations. And quantum electrodynamics was renormalizable in this sense. Now, you might think, well, this is a terrible drawback because we'd like a method of dealing with infinities that works for any theory. I didn't feel that way. It seemed to me that the criterion of renormalizability imposed a kind of simplicity on a theory, which otherwise would be just guesswork, which allowed us to identify the one correct theory out of the infinite variety of possible theories. For example, in quantum electrodynamics, if you just assume there are electrons, there are photons, they obey certain symmetry principles, Lorentz invariance, gauge invariance, you can still have an infinitely complicated set of field equations in which you can not make any predictions. And yet, when you impose the condition of renormalizability, the theory is forced to be simple and you can actually use it to make calculations, as for example, a calculation of the anomalous magnetic moment of the electron, which was done in 1948, turned out to agree magnificently with observation to many decimal places. That calculation could not be done without imposing a condition of simplicity on the theory. And the only principled reason for imposing that condition was the demand that the theory was renormalizable. That's what we wanted in our theory of weak and strong interactions. But unfortunately, the only existing theory of weak interactions we had was not renormalizable. It predicted infinities for anything beyond the lowest order of perturbation theory that could not be eliminated by a renormalization of the parameters of the theory. The strategy that many of us adopted at that time was simply to bypass the whole issue of finding the detailed dynamical theory and instead make use of a kind of principle that we hoped to find validated that allowed us to make predictions without knowing the underlying theory. It was like having a spy in the camp of an adversary army. We weren't actually fighting the army, but our spy was reporting to us on things that we could understand without actually fighting a battle. The spy was principles of symmetry. Principles of symmetry, of course, had been studied by mathematicians and scientists for many centuries, going back to Plato's work, trying to identify the regular polyhedra with the atoms of the elements. In the 19th century, principles of symmetry were developed in a more scientific way as a basis for example, crystallography. The symmetries were always incidental properties of the underlying theory, and were known about because we knew the theory, as, for example, we had a theory of crystals. Starting with the work of Einstein in the 20th century, symmetries became a subject of investigation in their own right as a possible basis for physical theories, so that Einstein demanded that physical theories obey the symmetry principle that the laws of nature look the same from all uniformly moving laboratories. By the time of which I've been speaking, the 1950s and 1960s, we knew about a number of symmetries of the weak and strong and electromagnetic forces, even without having a theory of anything but electromagnetism. There were, of course, Lorentz invariants, the basis of Einstein's special relativity, which is related to the conservation of energy, momentum, and angular momentum. There was electromagnetic gauge invariance, apparently an exact symmetry of everything, which is associated with what appears to be an exact conservation law, the conservation of electric charge. There were symmetries that appeared to be related to exact conservation laws, the conservation of baryon number and lepton number, all of which were at that time believed to be exact conservation laws governing all interactions. But there were also symmetries, and this was very peculiar, that were only symmetries of parts of nature. There was a symmetry called charge independence or isotopic spin symmetry, or SU2, which was a symmetry of the strong interactions, but not of the electromagnetic and weak interactions. There were symmetries like charge conjugation invariance, left-right symmetry, the conservation of quantum numbers called strangeness, that appeared to be good symmetries of the strong and electromagnetic forces, but not of the weak interactions. And there were even symmetries that didn't even appear to be exact symmetries of anything, like the so-called eightfold way or SU3 symmetry. Some of us got enthusiastic about the idea, and this goes back to 1960. Some of us got enthusiastic about the idea that there are lots of symmetries in nature that we don't yet know about, because although they are symmetries of the underlying equations, they're not symmetries of the solutions of those equations. In other words, they're not symmetries of the physical phenomena described by the solutions of the fundamental equations. These are so-called spontaneously broken symmetries, which may themselves be exact or approximate, but have implications different from those of the ordinary symmetries. One of the implications appeared to rule out the whole idea. It was shown in 1961 and then more mathematically rigorously in 1962, that whenever you have a spontaneously broken symmetry, you get massless particles. One massless, and these not only have no mass, but they have no spin. You get one of these particles in nature, this not just in the equations, but actual particles that can be observed for each broken symmetry. This seemed to put an end to the whole idea. An exception which turned out to be tremendously important to this theorem, was then discovered theoretically 2 years later in 1964 by a number of theorists that led to, what is called the Higgs mechanism, that this conclusion that there are these massless particles for every broken symmetry, particles called Goldstone bosons, is not valid if the underlying symmetry is of the type typified by electromagnetic gauge invariance, a symmetry involving a massless field of spin 1, like the electromagnetic field. In that case, the Goldstone bosons, although they appear in a sense in the equations, in nature they go to form the part of the particles described by these fields like the electromagnetic field, giving the quanta of these fields a mass. This was an exception to the theorem that there had to be a Goldstone boson for every broken symmetry. But its importance was not realized at the time. It wasn't applied to any particular physical force. And I think this was in part because the idea of spontaneously broken symmetries, which are not of the type like electromagnetic gauge invariance, but are so-called global symmetries, which act in the same way everywhere in space and time, like isotopic spin symmetry. The idea that these symmetries are only approximate and in addition are spontaneously broken began to have tremendous success. We developed a theory of the interactions of precisely the Goldstone bosons, which are not massless because the symmetry wasn't exact to begin with, and in fact are identified as the lightest of all the strongly interacting particles, the pi meson. And a lot of us had fun in the mid-1960s developing theories that went beyond isotopic spin, approximate symmetries of the strong forces which are spontaneously broken, which account for the existence of pions. In a sense, this was the originating idea of spontaneous symmetry breaking. It was all working very well, and the theoretical results actually agreed with experiments. I was, since Professor Rosenfeld was kind enough to mention my 1967 paper, I'll say a word about how from this I was led to that paper. I was fascinated by these symmetries and was conjecturing that perhaps, in a sense, they were like electromagnetism. They were of a type called Yang-Mills symmetries, which are symmetries whose action varies from place to place in space and time. And I tried to make, using the symmetries that we had been exploiting in the theory of low energy pi mesons, I tried to make a Yang-Mills type theory of strong forces in which particles like the rho meson, which is a spin 1 particle of negative parity, and a partner called the A1, which is a spin 1 meson of positive parity, would be generated through the Higgs mechanism. I didn't know about the Higgs mechanism at first, but it reappeared in the theory, and they had already done this 3 years earlier. It didn't work. I was very depressed by this because although there was a massive particle that came out of the calculations, like the A1 meson, the rho meson, which was a much better known particle, very well established, responsible to some extent for strong interactions through its exchange, stubbornly remained massless. And at a certain point, I realized I was just working on the wrong problem, that instead of working on the strong forces, I should be working on the weak forces combined with the electromagnetic forces. And this massless rho meson wasn't the rho meson at all. It was the photon, the quantum of electromagnetism, which really is massless. And its heavy partner was not the A1 meson, which may or may not exist actually, but it was the W particle, which since time immemorial had been thought to, whose exchange had been thought to generate the weak interactions. And I developed a theory of the combined weak and electromagnetic forces. At that time, I didn't feel I really understood anything about the strong interactions. So I decided just to limit myself to the electromagnetic and weak interactions of leptons, that is electrons, neutrinos, and their heavier partners. And the first sentences of that paper said, leptons interact only with photons and with the intermediate bosons that presumably mediate weak interactions. What could be more natural than to unite these spin 1 bosons in a multiplet of gauge fields? Gauge fields are fields like the electromagnetic field. Well, what indeed would be more natural? So I went ahead and did it. Just sticking to the leptons, it became fairly obvious what the symmetry group had to be. And in fact, it had already been used in a somewhat different way for studying weak interactions by Glashow and by Salam and Ward. The theory, the group is, for those who care, SU2 cross U1. The theory predicted a bunch of particles that were new in the sense that they hadn't yet been observed. The W particle, well, that was an old speculation, but with an electrically neutral particle as its partner, I call the Z, and with a prediction of their masses. Well, the two masses were predicted in terms of a single unknown quantity, but both were predicted to be heavy enough, heavier than 40 GeV, so that they wouldn't have been discovered yet anyway. And also the theory predicted a spinless, electrically neutral particle, the one that has become called the Higgs boson, all of whose properties were predicted by this theory, except unfortunately for its mass, which meant we didn't really know how big an accelerator you needed to produce it. The big question for a while was, is this theory renormalizable in the same sense as electrodynamics? Salam and I thought it was, and but we weren't able to prove it. I tried hard with a student to prove it. I was using a too limited mathematical framework. Finally, in a different mathematical framework, the proof was given in 1971, initially by Gerardo 't Hooft, and then by 't Hooft and Veltman, and by Ben Lee and Saint-Justin. And after this work, it became clear that this was the kind of theory we had hoped for all along. It was a renormalizable theory, which meant not only that the infinities could be eliminated by a redefinition of the parameters of the theory, which of course we needed, but also that there was a symmetry imposed on the theory by the criterion of renormalizability that would allow you to actually do calculations, because you couldn't put in every term in the field theory that was consistent with the symmetries. In the early 1970s, the theory was worked out. I and others worked on applying this also to strong interactions. And one of the key predictions of the theory were in addition to the familiar weak interactions in which protons turn into neutrons, transferring charge to the leptons, producing an electron or a positron, there were so-called neutral current weak interactions transmitted by the Z particle. And that was a key prediction of, we calculated that these neutral current processes would just barely have been visible, and they were not by any means ruled out by the experiments at that time. Then in 1973, they were discovered, and it turned out that their properties just agreed completely with the theory. The next big step, so by the end of the 1970s, there was general agreement in that the weak and electromagnetic interactions together were described by this theory. Salam had developed this theory independently in 1968. The next big step in developing the standard model of elementary particle physics was to tackle the strong forces. It was known experimentally that they get, apparently the effective strength decreases with energy. A number of theorists went to work trying to find a theory like a renormalizable gauge theory, like electrodynamics or the electroweak theory, that would account for the weakening of strong interactions at very high energy. And it was shown in 1973 by Gross and Wilczek, and independently Politzer, that the kind of theory that has this property is the same kind of gauge theory called a Yang-Mills theory that had worked so well in electrodynamics and weak interactions. Of course, with a different group acting on quarks, but not on leptons because they don't feel the strong forces. It was a theory based on a group, SU3, which predicted an octet of photon-like particles, which we call gluons, because they were supposed to glue the quarks together inside the proton and neutron. If with a Yang-Mills theory, like electrodynamics, we would expect massless gluons. And of course, these could not have evaded observation because they're strongly interacting. And if they're massless, it doesn't take much energy to produce them. And we certainly had never seen them. It was because of the success of applying the Higgs mechanism, that is the spontaneous breaking of the gauge symmetry in the electroweak theory. At first, it was generally expected that the gluons were very heavy, given their mass, like the W and Z, by the Higgs mechanism. A little bit later, I think no more than a few months later, it was suggested that in fact, that's not true. The symmetry is not broken. The gluons are massless, but particles that carry the quantum numbers of this group, SU3, quantum number called color, can't be pulled apart from each other because the forces get strong as you go to large distances. And as a result, you can never isolate colored particles, which explained, incidentally, why no one had ever seen quarks either. And this has become the standard wisdom, although no one has ever mathematically proved that in these theories, colored particles can't be isolated from each other. Now, the discovery of quantum chromodynamics as the theory of strong interactions opened up a number of very exciting possibilities. One was the fact that because the strong interactions become weak as you go to very high energy, actually the decrease is very slow. The coupling, the analog to electric charge, decreases with the inverse square root of the logarithm of the energy. So it's an extremely slow decrease. But there might be some very high energy, it would have to be very high because the decrease is so slow, where the strong coupling has decreased to the point where it's comparable to the weak electromagnetic forces. So at that energy, there might be, as had been previously speculated before the advent of quantum chromodynamics, there might be some energy where all the forces, weak, strong, and electromagnetic, come together with the same interaction. This suggested a new scale in physics called the grand unification scale, for obvious reasons, which would be of the order of 10 to the 15 or 10 to the 16 GeV, not very much lower than the energy scale called the Planck scale, at which the strength of gravity becomes comparable to the other, to the strengths of the other forces. Another possibility was opened by quantum chromodynamics. I was very excited when this theory was suggested by the fact that if you take this gauge theory of strong interactions and impose the condition of renormalizability and do not introduce scalar fields of the kind which would be needed to produce the Higgs mechanism and break the symmetry, but leave the symmetry unbroken and leave scalar fields out of the theory, then the theory of strong interactions automatically would conserve the symmetries like charge conjugation invariance, strangeness conservation, and aside from some qualifications I won't go into, left-right symmetry. So in other words, the fact, and the same was true incidentally of the electromagnetic interactions taken by themselves. So the fact that these would be good symmetries of the strong and electromagnetic forces, but not symmetries of the weak interactions, suddenly became obvious. These are not symmetries of the weak interactions because they're not fundamental symmetries at all. There's no reason why they should be symmetries of the weak interactions. They happen to be symmetries of the strong and electromagnetic forces because there is no way that the theory can be complicated enough, given the requirement of renormalizability, to violate these symmetries. Beyond that, there are other symmetries which had been thought to be exact symmetries of everything, including baryon and lepton conservation. The symmetries, for example, that prevent protons from absorbing an electron in the hydrogen atom that are responsible for the stability of matter. These symmetries are also accidental in the same sense. That is, taking the strong electromagnetic and weak interactions all together, imposing the condition of renormalizability, which provides a principle of simplicity. These theories cannot be complicated enough to violate the conservation of baryon and lepton number. So these conservation laws were also explained. Now it goes beyond this, because at the same time that all this was coming together, we were rethinking the status of renormalizability as a fundamental physical principle. The idea was beginning to take hold that all of these theories, of which we were so proud, are just effective field theories. That is, they are low energy limits of some underlying theory, maybe a grand unified theory, maybe something that isn't a theory, a field theory at all, like a string theory, because we began to realize any theory that satisfies the fundamental principles of quantum mechanics and relativity and a few other plausible assumptions will look like a renormalizable quantum field theory at sufficiently low energy. But there would inevitably be corrections to our effective field theory of strong, weak, and electromagnetic interactions, which would not be renormalizable, but would be very small because they're suppressed by powers of 1 over m, where m is whatever fundamental mass you think underlies the whole thing. It might be a grand unification mass like 10 to the 15 or 16 GeV. It might be the Planck scale of 10 to the 18 or 19 GeV. And so this opened up the possibility that there may be much more that we should be looking for involving lepton and baryon non-conservation. And indeed, lepton non-conservation has been discovered in the form of very small neutrino masses. And these neutrino masses of the order of hundredths of volts in energy units are just about as small as you would expect on this basis, suppressed by 1 power of 1 over m, where m is something like 10 to the 16 GeV. There is another kind of violation of baryon and lepton number, which would also be very weak, suppressed by 2 powers of 1 over m, that would result in the spontaneous decay of the proton, or any other nucleus that's usually thought to be a stable nucleus, like carbon-12 or oxygen-16. And this has not been seen, but I think should be searched for. Well, I said it has not been seen, but in a sense it has been seen, because the universe, and now I'm coming back to cosmology, the universe obviously is not neutral between matter and antimatter. There was a time when the temperature was above hundreds of GeV, when there would have been as many protons and antiprotons as photons. Almost all of them have annihilated, but they haven't all annihilated. We are left with about 1 baryon, proton or neutron, for every billion or so photons. A tiny admixture of heavy particles, protons and neutrons, which have no antiprotons or antineutrons around to annihilate with, and so are left over. Why is there this imbalance? Well, it may, and I think it does, have something to do with the fact that baryon conservation is not a fundamental symmetry of nature any more than left-right symmetry or charge conjugation and the matter-antimatter symmetry or many of the other symmetries we deal with. It is simply, its violation is highly suppressed by 2 powers of 1 over m, where m is an enormous mass. And we haven't seen it, except that we see a universe which is obviously non-symmetrical between baryons or antibaryons. Well, this shows how particle physics and cosmology come back together, and they come back together in other ways. In 1979, the idea began that the ordinary Big Bang theory that I described earlier, leading to nucleosynthesis at the end of the first 3 minutes and so on, was preceded by a period of exponentially rapid expansion called by Guth inflation. And this solves a number of cosmological problems, including the uniformity of that we see in nature. And it suggests that there was an early time when the energy density in ordinary space was enormous. And how big? Well, something like a Planck mass per cubic Planck radii. In other words, the same scale converted into an energy density as we speculate about when we talk about a fundamental scale of grand unification or quantum gravity. And we have no hope of ever reaching those scales directly in our accelerator laboratories. In a sense, we have already reached that by observing these tiny neutrino masses, as I mentioned earlier. But for direct observation of physics at that high energy scale, I think we will have to rely on cosmology. That is, on looking for relics of the early period of inflation, which have survived to the present. And we already see such relics in the inhomogeneity of matter, which was responsible for galaxies and clusters of galaxies. And we hope to see, although it hasn't been found yet, gravitational radiation coming from that earlier period of inflation, which would provide direct evidence of physics at the really fundamental scale. So now at that time, the energy in empty space was enormous. That's the whole idea of inflation. Now it's very small. We don't know for sure why it's so small, but an idea has emerged. It's not zero, because in fact, although in the 1930s, astrophysicists were mostly concerned with trying to estimate how fast the expansion of the universe was slowing down due to the gravitational attraction of its constituents. In 1998, astronomers discovered that in fact the expansion is not slowing down, it is speeding up. And this is attributed to a very tiny energy density empty space, incredibly tiny by the scales of elementary particle physics, even ordinary elementary particle physics, like what goes on in atomic nuclei, let alone elementary particle physics at the fundamental Planck or grand unification scale. Why is it so small? That has remained a tremendous mystery, and the answer may be found in the physics of the period of inflation. According to one version of that chaotic inflation, the universe did not result in a single smooth expansion, but in many sub-universes, like what we call the universe, many big bangs going off here and there, and in which perhaps, we don't know because we don't know the physics of this period of inflation, perhaps resulting with different values of fundamental constants. And it may be that in just such, that in the great variety of big bangs, the fundamental constants are not suitable for the existence of life. For example, if this dark energy which pervades the universe, which we see causing the expansion of the universe to accelerate, if that were much larger, then galaxies could never form. Stars would not form, planets would not form, there would be no living creatures. Only in a very tiny minority of big bangs are conditions just right for life to appear, and naturally, that's the kind of big bang in which we find ourselves. I don't know if that's going to be the final answer, but as elementary particle physics has so far not suggested any solution to the problem of the dark energy, and the values, the back of the envelope order of magnitude calculations that it suggests are hopelessly too large. So we may be forced into just this kind of so-called anthropic explanation. But in order to verify that, we have to be able to see better into the period before the ordinary Big Bang, into this supposed period of inflation, using both the eye of theory, if we can make progress in understanding quantum gravity, perhaps with string theory, or the eye of observation, observing further relics of the very early universe. Thank you. I'll be glad to take questions.
Thank you very much, Professor Weinberg, for this excellent colloquium. And so people can write questions in the chats. We can do that. And at the moment, I have one question already from Professor Nathan Berkowitz. He's asking the following.
Oh, hello.
He's probably watching it. So 50 years ago, renormalizability was used as a rational principle for explaining why field theories such as QED and the Standard Model are simple. But the modern view is that these theories should be interpreted as an effective field theory where renormalizability is automatic. Do you expect that the fundamental theory underlying this effective theory should be simple? And if yes, what would be the rational principle behind this expectation?
I think it should be simple, because if it isn't simple, the hell with it. That is the kind of theory that we aim at in doing theoretical physics is not necessarily a renormalizable quantum field theory, but it has to be a simple theory, because otherwise there's no purpose in our aim. If every year we get a book from the Lawrence Berkeley Laboratory listing all the properties of the known mesons and baryons and so on. It's become a very heavy book, like an old-fashioned telephone book. If that's the fundamental theory, just a list of numbers, then it's not interesting. We don't want it. It may be true, and in fact, the Lawrence Berkeley Laboratory doesn't publish false numbers, but it's not what we're looking for. So we will go on looking for a simple theory. And the real question, it seems to me, is, are we smart enough to find it? I don't know that we are. The simple theory, just as quantum mechanics is beyond the mental ability of dogs, or even of pigs, which I understand are much smarter, the underlying simple theory may be beyond our intellectual capabilities. But unlike dogs and pigs, we can join our minds in using language. And so the comparison is not with an individual human being, but with the whole connected mass of billions of human beings. And I'm guessing, well, that's the guess on which I base my life, that collectively we are smart enough.
Thank you. But so you think it's simple, but is there any rational principle why you think it's simple? In addition,
Beyond what I've said, no.
okay, good. So there's another question by Professor Andrew Lessa. The question is this: you have successfully applied the entropic principle to predict the cosmological constant. What is your current view on the entropic principle and its use to solve particle physics questions?
Well, other people have used the anthropic arguments to explain the pattern of quark masses. Obviously, if the proton and neutron are built up out of a pair of quarks, a so-called up quark and a down quark, and if the down quark was much heavier than the up quark, then or much lighter than the up quark, the chemistry that would result would be entirely different and very likely would not allow the evolution of life. I hope all these arguments will turn out to be irrelevant, including the argument on the dark energy. Because like any good theoretical physicist, I want to calculate these things, not just get the right order of magnitude or the right hierarchy of masses, but actually predict what the masses are, what the vacuum energy is, eventually with high precision. That's what we all hope. And anthropic arguments can never do that for you. So I think because of the possibility of a multiverse of many big bangs, which is provided by chaotic inflation, I think we have to take anthropic arguments seriously as a possibility. And it may be that they are the only explanation we will ever have. Just as, I mean, to take an illustration, what is the explanation of the fact that the Earth is 93 million miles from the sun? Well, there is an anthropic explanation, which is if it was much closer or much farther, we couldn't have evolved. The water would be solid or would be gas. There wouldn't be any liquid water. That doesn't predict the 93 million miles. It only gives you an order of magnitude. Well, it gives you a range of possible distances. In fact, we have never done better than that anthropic argument because, in fact, and we also know that it's a valid argument because we have not just one planet in the universe, but countless billions of planets, some of which are too close to their star for water to be anything but a gas, and others too far for it to be anything but a solid. So the anthropic argument makes sense for the distance of the Earth from the sun. We wish we could do better. We wish, as Kepler did when he was a young man, we wish we could actually calculate from first principles how far the Earth is from the sun, but we can't. It's a historical accident. The best we can do is the anthropic argument. And we may wind up with that situation in fundamental physics, but I don't think we should assume that that's true. I think we should continue efforts like string theory to get a specific predictions, maybe not of everything, maybe some things will always be only anthropic, but we should try as much as possible to predict as much as we can with the kind of precision that we find in quantum electrodynamics and that we hope for in physics in general.
Okay. So I understand we're running late because I have to leave the room. So there are many other questions. I just asked.
No, we have a few. We have 5 more minutes according to the authorities here.
Okay. So one question, and then we'll see how it goes. So our field is in a strange moment right now, especially concerning the standard models. So they're all working too well in some sense. So we're drowning data. We have data from the LHC. We have data from several large-scale structure surveys, the CMB, and there's no indication of physics beyond the standard model at the LHC. Okay, there's dark matter, etc., but at accelerators, we don't have any evidence so far. So what do you think are the guiding principles to go beyond We don't have a guiding principle now, I think, to go beyond the standard models. And what do you think is going to happen, for instance, if the LHC does not find any new evidences for physics beyond the standard model?
Well, I'm afraid, of course, it's premature to reach that conclusion because the LHC is going to continue with upgrades, and it may yet discover the dark matter particle, or it may yet discover signs of supersymmetry. We don't know. But if it continues and does not accomplish any of these goals and discovers nothing beyond the standard model, I think physics, including experimental physics, will continue, but it'll be very hard to sell governments on the idea of building another accelerator. And in fact, I referred to this in the title of an article as the crisis of big science. But there are other things that can and should, and I think will be done. One of them I mentioned is the search for proton decay. I think that's been somewhat neglected. I think the rough estimates we can make of the rate of proton decay suggest that it's not hopelessly beyond our reach. We don't have a precise estimate, but I think it's worth pursuing in these big tanks of liquids underneath the Earth's surface, which are watched carefully for neutrinos. I think they should continue to be watched also for proton decay. And then, of course, there is astronomy. We've had a wonderful example of the excitement in astronomy just in this last week with this discovery of coalescing neutron stars observed in X-rays, in visible light, in the leftovers of the coalescence, and in gravitational radiation of all things. So astronomy is in the kind of golden age now that elementary particle physics was in the 1970s, and where countless discoveries are being made that are very relevant to theory, which theory is capable of dealing with, but is continually being inspired by. And some of these discoveries, I think, will bear on elementary particle physics. I mean, after all, we only know about dark matter and dark energy because the astronomers have told us about it, and they may learn more about it. The experiments on dark energy that are going on now, including one search here in Texas at the McDonald Observatory, may tell us whether the dark energy is evolving in time. And if it is, then the study of that evolution will be enormously exciting for particle physicists as well as astronomers. So there's lots. Science is nowhere near a frustrating end. Accelerator physics, I don't think is either. It may come to that point, but it will be because it's so hard to get governments to continue to pursue the high energy frontier. And as I said, I hope that doesn't happen either.
Okay, so Professor Weinberg, on behalf of the Brazilian Physical Society and all the people that assisted your talk, we thank you very much for your time and for this brilliant exposition. Thank you very much.
Well, thank you for your time and listening to all this, and I've enjoyed it very much.
Okay, goodbye.
Goodbye. Okay, thank you, Lara. And thank you for giving me the